All right, let's get started. Another Friday. All right, we're gonna be 2 out of the 15 weeks done already. I'm sure it'll continue to go fast. At least it's going fast for me. A short recap, right? We finished off stress on Wednesday. Shear stress, normal stress, right? Force perpendicular to a cross section, a force parallel to a cross section. Then we lastly jumped into this idea of, okay, well, sometimes we connect things at planes or surfaces that aren't perfectly perpendicular or parallel to the force, right? They might be at some arbitrary angle. And so what does that mean? Well, that just means that we have components of both a force that is parallel to that surface and normal to that surface based on our resultant force, right? And we figured out that what those components were based on what our angle was, beta, right, or theta. And then we noted the fact that as this cross section, right, that surface moves from completely perpendicular to completely horizontal, the area of that cross section, right, which stresses force over an area, the area changes, and so we need to account for that based on that angle. And so we came up with a couple equations that gave us our stress based on this force with respect to our given beta angle, as well as the area of the surface over which that acts, whether the force is in shear or in a normal force, right? We got a sigma n or a tau n for our normal and shear stress, okay? So after all of that, you guys have everything you need to do the homework. I'm sure all of you have started the homework, right? Yeah. Due on Wednesday, all right? We'll set up a quiz, which I'll open up towards the end of next week, and I'll talk to you a little bit about more about that on Monday. Just again, making sure that you guys can get out there through D2L and access the textbook. Make sure you can do that at least by the early next week, so that we can make sure you have access to the quizzes, which will be run through that platform also. So, which you'll access through D2L. Any questions on stress? No? Okay. We're going to jump into now chapter 2 of the text, which talks all about strain. What is strain? Well, strain is a quantity used to measure or describe, instead of the intensity of the force, but the intensity of deformation. So we'll call this quantity used to measure or describe the intensity of deformation. Right? Where deformation is really just a change in dimension. So if we had this block, if you looked at this block of material, okay, and we imposed upon that block of material a force P, right? We tried to pull this block of material apart. I think we would all just intuitively see that our block would then get longer, right? And I touched on this property called Poisson's ratio, which is this idea that we kind of have a conservation of mass, right? So if this stretches outward, right, we're going to get some level of shrinking in the opposite direction, right? So this would be our new cross section if we were pulling on this block with some force, right, and tension, pull it apart. So we get this deformation due to a load, right? You sitting in your chair, all of you, right? If you lean on the back of the chair, it moves a little bit, right? You impose a force on the back of the chair, and that force then creates deformation. Well, that deformation, in order to measure the intensity of deformation, we then calculate what we would call strain, right? Me walking around up on the podium here, right? The floor below me is deforming at some level due to the force that I'm applying to it. And so again, based on force, we separate strain into two main categories. We have normal strain and shear strain. As you can imagine, normal strain comes from the normal force, right? Or normal stress. Shear strain comes from shear stress or shear force. So normal strain is what we call our change in member length or width. That results from normal stress. All right, so that block that we applied a normal force to, right, there would be a normal stress, right, a sigma in this block. We could calculate that at this point. Well, that normal stress creates a change in our member length or width, and we would then subsequently have normal strain. Shear strain is an angular distortion property. And it results, as you can imagine, from shear stress. So if we step back to looking back at our sign convention for our normal and shear stresses, okay, if you remember, positive normal stress, right, sigma, is when our stress or force is acting away from our surface, our normal surface. Negative normal stress is when our force or our stress is acting towards the surface. Whoops. Shear stress is positive when we get this distortion that pushes, say, a block of material up and to the right. Negative just being the opposite of that, so we get up and to the left, right? Or down to the right and down to the left, depending on which way you want to look at it. So if we looked at deformation associated with these stresses, right? If we had a block, right? We have two blocks like we have up above. We have some sort of normal force or normal stress acting away from and towards our surface. Right? We're going to get some deformation, as I mentioned. Right? You might get some thinning of our material and elongation of our material when we're trying to pull something apart. Conversely, we're going to have something like this happen when we try and squish something, right? So it's that deformation, say the elongation or the shortening of our block, that is what we would call our normal strain. Similarly, right, we have two directions for shear stress. So we would have two directions for shear strain. If we have a positive shear stress, it's it's going to do something like this to our existing block. And our deformed shape would look something like this, right? So with normal strain, we look at change in deformation, right, of length or width. For shear strain, we look at angular distortion, right? A shear stress or a shear force is going to essentially distort this at an angle, like make it rotate. And that rotation is what we would call our shear strain, right? Or the intensity of deformation from our shear force. So what does that look like? Well, in 2.2 in the text, they talk about normal strain, the definition of which, right? It's a deformation parameter. We call it epsilon. And it's delta over L, right? Epsilon is delta over L, and that is our change in length over our original length. Can't stress this enough. It's the original length, okay? So if we were going to be doing normal strain, let's say we want that block up above, right? We would take the change in length, right? The distance that top of the block moved, and we would divide it by the original height or length of our block, right? Not the new length of our block. So it's our change in length over the original length, and that will give us a parameter, normal strain, which is a measure of the intensity of deformation due to a normal stress or normal force. What are our units? Well, if you look at the equation there, right, we have change in length over original length. So it's really length over length. Could be inches over inches, meters over meters, right? Those are effectively the same thing though, right? It's unitless. It's a length over a length. But it's usually denoted in inches over inches, and a few other here we'll talk about in a second. So what is a positive strain? Well, if you look back at our normal stress, right, it follows the same suit as our normal stress sign convention. So if we get a positive normal stress, right, which results in tension, which results in elongation of our material. And when we get elongation, we have a positive strain. Right, so if it gets longer, we have a positive strain. Inversely, as you can imagine, we have a negative normal stress, right? We have compression. Resulting in shortening. And our strain then becomes negative. So if I gave you a strain of 0.002, right, and it was positive, you would know that the element with which we were looking at or material we were looking at got longer. If it was negative, you know that it was shortened, right? It got smaller. And you would know then also that the stress within that element is going to be in tension because we get that elongation. And if it was negative, we would know that it would be in compression. As I mentioned, the units, right, are inches over inches, meter over meter. Oftentimes, it's denoted as what we would call microstrain. So it'd be mu meter over meter, or mu inches over inches. What does that mean? Well, it's just an easier way of making the number bigger, because strain is generally very small, right? So it might be like literally like 0.002 inches per inch, okay? So in order to denote that as a larger number, we would call it, say, microstrain. So we would say 2,000 microstrain is the same as 0.002. 0.002 inches per inch equals 2,000 micro inches per inch, right? Which is the same as saying 2,000 micrometers per meter, right? It's unitless. It's just a length over a length. Doesn't matter what system or customary units it's in. Sometimes it's also referenced as a percentage. What would that be? Well, if we had the strain, or epsilon, equal to 0.2%, well, that's the same as 0.002, right, inches per inch, which is the same as meters per meter, right? Just move the decimal place over 2. So sometimes it's easier to denote this. We got less decimals to worry about, right? Sometimes we go a bit further, we call it microstrain. We would denote it in thousands, usually. But all meaning the same thing. All right, let's do an example. What are they giving us? Well, they're saying that we have an axial bar that's loaded on the ends. It has 2 different segments. Okay. One segment length is 1.2 meters. The other one is 2.8 meters. We had some force P. They tell us that the total elongation between joints A and C is 7.5 millimeters. What we would call that? Well, that would be our delta total, right? A to C equals 7.5 millimeters. What else do they give us? Well, they say the segment lengths. They also say that the normal strain in segment 2 is 2,075 micrometers per meter. So epsilon from B to C, right, that's segment 2, is 2,075 micrometers per meter. Well, what does that equal? Well, if we move that 10 to the negative 6, that'd be 0.002075 meters per meter, right? So you can see microstrain can be helpful so you don't have to deal with all of the decimals. And they want us to find a couple things. One, they say we want to know what is the elongation of segment 2, and then what's the normal strain in segment 1. Well, if we start with A, they want to know what's the elongation of segment 2. Right? Well, what's the equation of normal strain? Anybody? Just gave it to you. Yeah, so change in length over the original length. So if we utilize that and say strain is delta over L, right? So this would be delta from B to C, length from B to C, and that would give us the strain from B to C, right? All attached to the individual segment that we're looking at. Well, we were given epsilon B to C, so we have the strain between B and C. Let's see what we know. We have that. We're also given that length between B and C, right? 2.8 meters. So we have that. And they are asking us for the elongation of segment 2. Well, that would be delta BC. That's the only thing in the equation we don't have. So what does that mean? Well, we can just plug and chug this whole thing out. So we got delta BC now equals the strain from B to C. Well, we decided was 0.002075 meters per meter, or millimeters per millimeter, or inches per inches. It's all the same. We're going to multiply this by the length from B to C, right? 2.8 meters. What does that mean? Well, our change in length, right? Rod 2 under this applied load got longer, right? The strain is positive, so that means we have elongation. So 5.81 times 10 to the negative third meters. While knowing that there's 1,000 millimeters per meter, this is the same as saying 5.81 millimeters. And that's the answer to part A. Okay. That's how far that rod 2 elongated due to the applied load, based on knowing 1, the length of the rod, and 2, the amount of strain in the rod, right? This is the intensity of deformation. So it's essentially how much does the bar move per inch length of bar, right? Inches over inches. So now if we jump to part B, they ask, well, what's the normal strain in segment 1 of the rod?
Do we really need to track units for strain? Because they always cancel out, do they not?
Correct.
So
Yep.
it's a unitless measure?
It is a unitless measure. Yep.
Okay.
Yep. You don't necessarily have to track units on strain. Correct.
Which seems like redundancy.
Yes, a little bit. For sure. But I think in general it helps you conceptualize and look back and know that it is unitless, and the fact that it is derived from dividing a length over a length.
Got it.
So if you're wondering what strain is, the units of meters over meters tells you that it is a length over a length, right? Which can be helpful. So we're looking for now, what is the normal strain in segment 1 of the rod, or the strain between A and B, right? So we have epsilon A to B. Well, that equals the change in length from A to B over the length from A to B. Well, I said we wanted to know what the strain was. As we knew for part A, right? We know the length of segment 1. Do we know the change in length of segment 1? Yes? No? We do, indirectly, right? Because they gave us the total length of the total change in length between A and C was 7.5 millimeters, right? Delta total, 7.5 millimeters. Well, we calculated what the delta was from B to C. And if they told us what the total delta was, we can figure out what the delta is from A to B. So if we do delta total equals delta A to B plus delta B to C, and we had 7.5 millimeters. We don't know what A to B is, but we do know what B to C is, 5.81 millimeters. That then tells us 1.69 millimeters is our change in length of segment 1. Now we have it, and it's as simple as plugging everything in. 1.69 millimeters divided by 1.2 meters. Well, there's a problem there, right? They have to be the same units. We need millimeters over millimeters or meters over meters. So I'm going to multiply by 1 over 1,000 to get this all into meters. We're going to get a strain from A to B equal to 1.408 times 10 to the negative third meters over meters. Well, that's the same as 1.408 millimeters over millimeters. So what does this look like? Well, if we looked at our bar after the fact here, got bar 1. We have bar 2. We had some force P on the ends. What does that mean? Well, we had some elongation here and some elongation here, right? This being our delta A to B, this being our delta B to C. So now our new length based on the applied force, right? We know that it's in tension because all of our strains are positive. So we know that this entire rod system got longer. Well, it got longer because we started at 4 meters, right? 1.2 meters plus 2.8 meters. So it'd be 4 meters plus our delta A to B, which is 1.69 millimeters, plus our our 5.81 millimeters, right? Why is this important? Well, as we'll find later on, right, deformations is a big part of whether or not things that we design as engineers are usable, right? They might be able to withstand the forces, but they might deform to a point where they no longer serve their purpose, okay? Like for CETs from the civil side with buildings, vibration is a big one. Right? If anyone's been in the sub ballroom when there's a bunch of people in there, the whole floor shakes, right? At some point, it has gotten so bad in that building that people don't want to be in that room because they feel like there's lack of safety. But in reality, it's strong enough. The floor is just fine, right? But it doesn't create an environment that people actually want to be in, okay? When you design like a building that maybe has an aerobics on one floor in one room next to a room that's more for offices, right? You have to take into account the fact that you're going to have all of this ambient activity next door. You wouldn't want to, obstruct the ability for the people in the offices to work, okay? On the MET side, like gears, bearings, alignments of shafts, all of those things, right? Shafts might be able to handle the torque applied to them, but if they deform too much, it might be so detrimental that it won't actually work, right? The system might actually not work. So that's where strains come in, and they're a big part of whether or not things are usable. Okay. Any questions on that one? No? Okay. Second example. We want to determine the strain in rod 1 if the strain in rod 2 is negative 0.003 meters per meter. Well, we're going to change this to feet per feet because I changed this example and I forgot to change that. What does that mean? Well, it's the same as negative 3,000 micro feet per feet, right? So we've got this bar system. We've got this very large horizontal bar. We're going to call it we're going to say that it's infinitely stiff. Right? It does not deform. No matter how much load or deformation we put in rods 1 or 2, this bar remains straight. So if we look at this system, and we'll learn as you guys will learn as we go through the course, right? In order to solve some problems, we need to look at the deformed shape. And that deformed shape will allow us, it provides us with a relationship between strains in varying elements in a system. So if we looked at our bar, for instance, we've got this pivot, right, at the end of it. So if it pivots on its end, as it rotates, right, rod 1 is going to get longer and rod 2 is going to get shorter, right, if it rotated clockwise. In this case, if we look at our strains, right, if we were given the strain in rod 2, is rod 2 getting longer or shorter? Shorter, right? Yeah. We have a negative strain, so rod 2 is getting shorter. So that means that this bar is going to rotate clockwise. So if we look at a simpler model, and we look at the undeformed, and then the, whoops, I guess this is only as good as I can draw a line. All right, so that would be the undeformed bar and the deformed bar. So if we had rod 1, it's going to be connected something like this, right? And then we have rod 2. It's going to be connected something like this. So we've got delta 1, right? The change in length of rod 1. And delta 2, all coming back to this pivot. So if you don't see it now, right, we have this similar triangles behavior going on, right? Where there's a ratio or a relationship between the deformation in rod 2 versus the deformation in rod 1. And we'll use more of these relationships later on when we start looking at axial bar systems or torsional systems. So we have this delta 1 and delta 2. Well, if we look back at our distances, well, this was 5 feet, and this was 5 feet. If we use similar triangles, right, we have a triangle that's sitting right here. We've got a triangle that's sitting right there, right? We've got these two triangles. Because they're similar triangles, right? There's a relationship between them. We can say that from that relationship, we can say that delta 2 equals 2 times delta 1, right? Essentially saying delta 1 to 5 feet is the same as delta 2 to 10 feet, which tells us that delta 2 is twice delta 1, or delta 1 is 1/2 delta 2. Well, now that we know a relationship between our change in lengths of our two rods, we have our strain equation, right, which relates the change in length of a rod over the original length. We have the original lengths. So if we start by saying, all right, the strain equals delta over L. In order to get the strain in rod 2, we need to figure out the change in length of rod 2. Right? Change in length of rod 2, or sorry, the strain in rod 1. We need to figure out what the change in length of rod 2 is based on our known strain. So we have delta 2 equals epsilon to L2. Right? The strain in rod 2 we know. We know the original length of 2. We can figure out our change in length of 2. Once we know the change in length of 2, we can plug it back into that equation, figure out our change in length of rod 1. We know the length of rod 1, we can figure out the strain in rod 1. So how does this look? Well, this goes something like this. So we had a negative 0.003 feet per feet. It's 2.5 feet long. So we get a delta 2 equal to negative 0.0075 feet. We know delta 1 is 1/2 delta 2. So 1/2 times negative 0.0075 feet. In this case, right, so this equals delta 1 equals negative 0.00375. Why'd I throw a negative on there? Any ideas? Yeah, right, it's getting longer. Right? Rod 1 is hung from up above. As we go clockwise, right, if rod 2 gets shorter, rod 1 gets longer. So I need to make the sign opposite. So now we have a positive delta 1 equal to 0.00375 feet. So we have epsilon 1 now equals delta 1 over the length of 1, 0.00375 feet, all over 4 feet. We get a strain in 1 equal to 0.000938 feet per feet, which is the same as saying we have 938 micro strain. Questions? So that's normal strain, right? Relates back to normal stress. We have this elongation or shortening depending on the sign, right? Whether our normal stress is positive or negative, we get a positive or negative normal strain. It's all relating back to, right, a normal force, which creates a elongation or shortening of our member. Well, like we have normal stress that creates normal strain, as I mentioned, shear stress or shear force creates shear strain. So 2.3 in the text talks all about shear strain. Well, as we mentioned, or as I mentioned, right, if we had a shear force, acting on an element, it would distort, right? We get an angular distortion of our element based on that shear force. And this right here, this angle with which our element distorts, gamma, is what we would call shear strain. Well, if we looked at the dimensions here, right? We're shearing this element and pushing it off to the side. It's going to deform some amount, right? It's going to distort some distance. Call that delta x. Yes?
So that gamma symbol is the same as the V, or what is it?
Up in that top corner that I did?
Yeah.
Yeah, that's supposed to be a gamma.
Okay.
Yeah. Let me try this again. Is that better?
Gotcha.
Sort of.
Yeah.
Pretty critical of my Greek symbols. Yeah, same thing. Okay, so that gamma is the same gamma up there, and that is denoted as shear strain. Okay, so instead of epsilon, now we have gamma. That shear strain is the angle, right? Well, if we use trigonometry here and we figure out what that angle is, well, that angle is a function of, right, the height of our element, right, the leg of this triangle, or the vertical leg, and the horizontal leg, right, delta x. All right, so if we go back and we say gamma, that's a gamma. Opposite over adjacent, right? So katoa, opposite being delta x, adjacent being L. We get this gamma is the tangent. What are the units of gamma? They are in radians. Anybody remember the relationship between radians and degrees? No? Yes? Hell yeah. All right, radians is degrees over 180 times pi. Right, there are 2 pi radians in 360 degrees. So there are pi radians in 180 degrees. Right, pi radians equals 180 degrees. What's the sign convention? Okay, knowing that our shear strain that we calculate is we're looking for this angle, right? Essentially the distortion of the edge of our block, okay? Which is really a function of this theta, right? We start out at 90 degrees, right? And we distort. In this case, we put a, right, this would be a positive shear stress, right, up and to the right. So we're going to have this theta 1, right? That's our initial angle. Theta 1 is going to be 90 degrees. And then based on oops, did that wrong. Goes like this, and like this, this, like this. Right? This is our theta 2, right? Theta 1 becomes theta 2 based on some applied stress or force, right? A shear force in our case. Well, if we put a positive shear stress, right, up and to the right, or just distorting it up and to the right, theta 1 is greater than theta 2, right? And if that's the case, our gamma is positive. So this would be a positive shear strain. Similar with normal strain, right? When we had a positive normal stress, we had a positive normal strain, we got elongation. We had a negative normal stress, we got a negative normal strain. Well, same goes for here. Right? But an easier way to visualize it, right? If you put a positive shear stress on it, this angle that does start out as 90, if it gets smaller, then it's a positive shear strain. If theta 1 is less than theta 2, then we get a negative shear strain. Right? That would look something like this. Up and to the left. Well, as we found from our normal strain calculations, right, we're dealing with very, very small deformation, right? 0.002 inches per inch, feet per feet, okay? So when we take this trigonomic function, right, tangent of delta x over L, right, this angular distortion, right, it's going to be very, very small. And what happens is when we're looking at very small angles, notably when delta x is a lot smaller than L, then delta x over L is a small number. And the tangent of delta x over L just equals delta x over L. So what does that mean? Well, that means gamma. That's a gamma. Is delta x over L. Or gamma equals pi over 2 minus theta 2. Right, if we looked at our, this is our gamma, and this is our gamma. So if we took our 90 degrees, which is pi over 2, and subtracted our theta 2, right? If theta 2 is less than theta 1, or 90 degrees, that's going to be a positive value. If it's greater than that, it's going to be a negative value, right? Or if we knew the distortion, right, the actual movement of our block or material, we could calculate gamma based on how far our block distorts horizontally over how far our block, or how tall our block was, right, or our material. All right. Have a great weekend. Don't forget the homework. Remember the EM Learning Centers out there. We've got our TA, Daruk. We got myself. Reach out if you have any questions.